Dear student, today we start another video lecture from Mechanics and Properties of Matter, chapter number 4, Properties of Matter. This lecture deals with another properties, important properties, that is Young's modulus, bulk modulus and modulus of rigidity. Before to start this particular point, we know that there are three types of moduli, and therefore there are three types of strain and stress. Therefore there are three types of moduli, and we starting from Young's modulus. And as we consider that three moduli, first of all we concentrate on longitudinal strain and longitudinal stress. And here the particular modulus, that is Young's modulus, that are related to the linear or longitudinal strain. In this strain, length get change, and when because of that applied deforming force or impact of deforming force, the particular length of that body gets elongated or contracted. And here when we use that word deforming force, that is suppose F, then deforming force per unit area called as stress, and change in length per unit length called as longitudinal strain. And here Young's modulus is defined as the ratio of longitudinal stress to the longitudinal strain, or linear stress to the linear strain. And using this definition, putting the value of longitudinal stress, that is F upon A, and longitudinal strain small l upon L, where small l is the change in length, and therefore rearranging the terms, Young's modulus Y is given by FL divided by AL. And here when we consider the unit of this moduli according to the particular formulae shown in 4.9, here Young's modulus has units in CGS system is dynes per centimeter square, and while in MKS system newtons per meter square, and the dimension of Y is that of stress. That means dimension of Young's modulus is similar to that of stress. And as here length get elongated, and we know that length only possesses by solid, and therefore only solid has a particular Young's modulus. Then after discussing Young's modulus, here we come to the another moduli, that is bulk modulus. And here when we consider the bulk modulus, then it is defined as the ratio of volume stress to the volume strain. That means in this type of moduli there is a change in volume. That means the deforming force is act in a such a way that there is a change in volume. And here by using the definition of volume stress, that is deforming force per unit area, and here this particular force is applied in a such a way that volume gets changes. Therefore this is the applied pressure, and here P is equal to F upon A, and volume strain is equal to small v upon capital V, where small v is change in that volume because of that applied deforming force, and capital V is original volume. And therefore using the definition of bulk modulus, it is denoted by the symbol K. We have F upon A divided by small v upon V. Rearranging the terms, we have F upon A is equal to pressure, therefore K is equal to pressure into original volume divided by small volume. And here when a very small pressure is applied, we can apply, instead of that P we can write dP, that means small pressure, and we have dP upon dV, upon V, or K is equal to minus dP by dV. And here when pressure increases, volume decreases, therefore dP upon dV is negative. And here the reciprocal of bulk modulus, that is 1 upon K, known as compressibility. Then after discussing this particular type of moduli, we came to the another type of moduli, last moduli, that is modulus of rigidity. And to obtain that modulus of rigidity, here we consider a solid cube as shown in this diagram. And here in this case, when we applied deforming force, then there is a change in shape. That change in shape known as shearing strain, and it is modulus. The modulus of rigidity is defined as shearing stress divided by shearing strain. That is the ratio of shearing stress, which is also called as tangential stress, because it is applied in such a way that tangent to that cube, and here therefore it is called as tangential stress. And the ratio of tangential stress to the shearing strain called as modulus of rigidity. And here consider a solid cube as shown in this diagram, that is AB, CD, EF, GH. The lower face CDGH is fixed and tangential force is applied F in such a way that the face ABEF, so that it is displaced to the position A dash B dash E dash EF E dash F as shown in this diagram. And here from particular diagram, each horizontal layer of cube is then displaced, and the displacement being proportional to the distance from the fixed plane, and then we have shearing strain is equal to displacement of plane divided by distance of the fixed plane. From that diagram, AA dash upon AD, but AA dash is equal to small l, AD is equal to original length L, and here according to the trigonometry, here that is equal to tan theta. And when theta is small, we know that tan theta can approximately written as theta, and therefore shearing strain is equal to theta. Then using the definition of modulus of rigidity, we have modulus of rigidity eta is equal to tangential stress divided by shearing strain. Putting the value of tangential stress F upon A, shearing strain theta, we have eta is equal to T upon theta, and here T is tangential force applied per unit area. And when we consider that unit of that particular modulus of rigidity is poise, and here the only solid possesses all three types of elastic constant, while liquid and gases possesses only one constant, that is bulk modulus. These are the three types of moduli, and each type of moduli related to each other, and therefore we concentrate on the another point, relation between three moduli, that is Young's modulus, bulk modulus, and modulus of rigidity. For this purpose, consider again when that cube having the each side unity, that is homogeneous isotropic material. This cube is homogeneous isotropic. That means this particular cube has same properties in all direction, and as we consider, each force will produce elongation in its direction, its own direction, and contraction in the opposite direction or perpendicular to it. And we know that Young's modulus is given by stress upon strain, and here in this case F upon 1, because unit length L is equal to 1, that divided by strain. Therefore longitudinal strain is equal to force upon Y. Similarly, by using the definition of Poisson's ratio, sigma is equal to lateral strain divided by longitudinal strain, and lateral compression strain Therefore, lateral compression strain is equal to sigma into longitudinal strain. Therefore, putting the values here, lateral compressional strain is given by sigma f upon y, say equation number 1. Now, here we consider or imagine that F2 is equal to F3 is equal to 0 and only one force F1 is acting, only one force F1 is applied, and here we have longitudinal strain along x direction and lateral compression strain along y and z direction. Lateral strains are equal and since material is isotropic. Similarly, when we consider F1 is equal to F2 is equal to 0, only F3 force is applied, then or if F3 force is present, then produces extension strain F3 upon y along z direction and compression strain sigma F3 upon y along x and y direction or axis. The elongation and contraction produces different forces acting simultaneously in different direction is tabulated in the below or in another slide. And here the particular diagram, particular table shows when we apply F1 along x-axis, what will be happened along x direction, y direction, and that of z direction. Similarly, when we apply F2 along y-axis, what will happen along the x, y, and that of z direction here. Similarly, because of F3 along z-axis, what will happen along each direction, along each axis that tabulated in this particular table. And here this negative sign indicates the contraction, positive sign indicates the extension. And here when we consider from the table the total elongation or extension along x-axis is addition of the three terms F1 upon y minus sigma F2 upon y minus sigma F3 upon y. But F1 is equal to F2 is equal to F3 is equal to F. Therefore, we have putting the values of F1 F2 each equal, we have F upon y into 1 minus 2 sigma. Putting this value using in equation number 1, we have volume strain is equal to 3F upon y into bracket 1 minus 2 sigma, say equation number 2. Similarly, volume stress is equal to F, and therefore using the definition of bulk modulus is equal to volume stress upon volume strain. Putting the value of volume stress and that of volume strain, we have K is equal to F upon 3F divided by y upon 1 minus 2 sigma. Again, rearranging the terms, here we have K is equal to y upon 3 into bracket 1 minus 2 sigma, and therefore again rearranging the terms, we have y upon 3K is equal to 1 minus 2 sigma. That means only considering along x direction the extension strain is adding each extension strain, we have this equation. Similarly, here when we consider the another table, when F3 is 0, what will happen? Here F1 stretches cube along x-axis, F2 compresses along y-axis. That means by considering these two forces are present, and here the extension strain and contraction strain because of F1, F2 shown in this table. Using the same concept, here we can obtain the total extension strain along x-axis is equal to F1 upon y plus sigma F2 upon y. Again, F1 is equal to F2 is equal to F. We have F upon y into 1 plus sigma. Similarly, the total strain along y-axis is minus F1 upon y minus sigma F2 upon y is equal to minus F upon y into 1 plus sigma. And again, we have considered F1 is equal to F2 is equal to F. Here compression strain along y-axis is equal to plus F upon Y into bracket 1 plus sigma. Thus, cube experience extension and contraction along that particular direction, and these are equivalent to shearing strain, that is angle of shear theta, and by considering shearing stress is equal to force per unit area F, that is equal to F, because A is equal to unity here in this case. And by considering such idea, we can write using the definition of modulus of rigidity, eta is equal to shearing stress divided by shearing strain, that is eta is equal to, putting the value of shearing stress and that of shearing strain, we have the particular equation. Rearranging the terms, we have y upon 2n is equal to 1 plus sigma. Therefore, sigma is equal to y upon 2n minus 1. Using this value of sigma in above equation, that is equation number 5, we have y upon 3k is equal to 1 minus 2 sigma, but instead of sigma we write y upon 2n minus 1. Then solving this bracket, we have y upon 3k is equal to 1 minus y upon n plus 2, minus minus become plus, and we have again rearranging the terms, simplify the equation, y upon 3k is equal to 3 minus y upon n. Again rearranging the terms, we have y upon k, that means by taking common, or we can write y upon k is equal to 9 minus 3y upon n, that means multiplied by 3 to each term. Here when we multiply 3 to y upon 3k, 3 get cancelled, we have y upon k. 3 into 3 becomes 9, 3 into y upon n minus 3y upon n. Again rearranging the terms, that means this minus term taking on the left side, we have y upon k plus 3y upon n. Again rearranging the term, taking y common, y into bracket 1 plus k plus 3 upon eta is equal to 9. And here rearranging the terms again, or simplify this equation, we have 1 upon k plus 3 upon eta is equal to 9 upon y, and this equation gives the relation between all three types of modulus: Young's modulus, bulk modulus, and that of modulus of rigidity. If we have know the values of two moduli, we can calculate third from this equation, and this equation plays important role in the properties of matter.